Bismillah Rahman Rahim. Assalamu alaikum. It's our new course on particle physics. Today's lecture we are just overviewing some problems related formulas which we are supposed to be done in our future videos. So there are some important problems from book Griffiths we are following. So important problems we have to cover in this series, and along with that, in today's video we just go through about their formulas which used. So let's start with problem number 5.2 in Griffith's book. So the formulas used in this problem is that whenever your L01, you have to use its value 1. Okay, this is the polynomial, Legendre polynomial. Whenever there is 0 in denominator, your answer should be 1. Okay, and spherical harmonics y00 should be equals to 1 by under root 4 pi. Okay, and if you already find the wave function and you need the Laplacian, you can say del. So how you can find? By using this formula. So del square f of r basically your wave function which you find before. So del square f basically equals to 1 by r square d by dr, and then r square df by dr. Okay, you have to take the derivative function, multiply by r square, then you have to take again derivative with respect to r. Okay, and your Coulomb potential must be equals to, you know, that minus e square divided by r, whereas a equals to h square by me square, where h is the Planck constant, m is the mass, and h is the charge of electron. So a becomes equals to h cut square divided by me square. Okay, whereas your energy in the first excited state is minus me4 divided by 2 h cut square. General formula of En is equals to minus me4 divided by 2 n square h cut square. But for first energy level, it should be n equals to 1, so it becomes minus me4 divided by 2 h cut square. Last, if you want to check your wave function normalize, so what you have to do, you have to do this. Okay, what psi square r square psi square, you have to take the mod square of your wave function which you before find, multiply by r square sine theta dr d theta d phi should be equals to 1. You have to prove this by using this expression. So this what you will use in problem 5.2. Now move towards next problem 5.3. In 5.3 again the Legendre polynomial, but here you can see in denominator this is 1 not 0. So if this is 1 not 0, so your answer should change. So your answer should be in this scenario is 2 minus r divided by a. Okay, now see L03, there is 3. This don't matters, but if there is 0 in denominator, so your Legendre polynomial is always equals to 1. Okay, now check this. Initially this is 0 0 0 0 equals to 1 by under root 4 pi, but what is your spherical harmonics in case of when your L value is 1? Okay, so this should be equals to under root 3 divided by 4 pi cos of theta. Okay, under root 3 divided by 4 pi cos of theta. Here the inclusion of 3 and cos of theta. But what if there is plus minus 1 in the numerator? So it becomes under root 3 by 4 8 pi now, not 4 pi, now 8 pi, and sine theta with the addition of e power iota m phi. M value is, you can see, 1, so it becomes e power plus minus iota phi. Understood? Now in problem 5.4, the formulas you have to use is this. First of all, you have to use the relativistic Einstein equation. You know that E equals to p square c square plus m square c power 4. Okay, in this problem what you have to do is that simple. You have to take this common, m square c power 4 you have to take common. Once you take common, then you just apply the binomial expansion. What is binomial expansion? 1 plus epsilon power 1 by 2. So it can be converted into 1 plus 1 by 2 epsilon minus 1 by 2 whole square 1 by 2 factorial epsilon square. Okay, this is, you have to apply binomial expansion. Okay, so in problem 5.6, this is the problem related to Lamb shift. What is Lamb shift? Lamb shift, in this you have to know about the two formulas in the S state and in the P state. So in the S state formula is alpha 5 mc squared divided by 1 by 4 n cube k n 0. Okay, But what in the p state is alpha 5 mc squared divided by 4 n cube. But now here is k and l, because here is l equals to 0, but here your l equals to, l has some value, so a k and l plus minus 1 divided by pi j plus 1 by 2 and l plus 1 by 2. Okay, whereas in S state this value is basically equals to 13.2, but in P state this value is approximately equals to 0.005, and we mostly we take it as 0. Okay, because here your n is 2, so k2 1 must be equals to 0, but if there is this here 0, because l is 0, then your constant value is 13.2. Okay, now move towards the next problem. In next problem, what we have to know about that is mass of mesons. If you want to find the masses of mesons, so what you have to do, this formula you have to use. The formula is that you can see here, mass of meson basically equals to m1 plus m2 plus a s1 s2 divided by m1 m2. Okay, and this mass is basically masses, and s1 s2 are the spins, and these are the masses. But this is the constant a. The value of this a is 159 as a bracket 2 mu divided by h cut. Mu means mass of up atom. Okay, mass of up quark whole square m mega electron volt per c square. Okay, and these are some constant values of mass of up quark, and mass of down quark is always equal, and that is 308 mega electron volts in quarks. Okay, in masses of mesons, and the strange mass is 483 mega electron volts. Okay, so the product in numerator, as you can see, s1 dot s2, this changes differently, because you know that mesons are two type of mesons. One are pseudoscalar mesons and one is vector mesons. Whereas pseudoscalar mesons is concerned, this product must be equals to minus 3 by 4 h cut square. But for vector mesons, the product must be equals to 1 by 4 h cut square. Okay, so once you put for pseudo scalar, once you put minus 3 by 4 here and putting the value of a, you get this answer for pseudo scalar m1 plus m2 minus 477 mu squared divided by m1 m2. Similarly, once you put the value of for vector mesons 1 by 4 h cut square here and putting the value of a, you get this expression for vector mesons. M is equals to m1 plus m2 159 mu squared divided by m1 m2. Okay, pseudoscalar mesons are like this: pions, chions, eta, eta prime. Okay, and vector mesons like rho, k star, phi, and omega. Okay, whereas the value of eta is this: 1 by 6 up quark, 1 by 6 down quark, plus 2 by 3 strange and strange anti strange. Okay, up anti up, down anti up, and strange anti strange quark. Eta prime must be equals to 1 by 3 up anti, 1 by 3 down anti, 1 by 3 strange anti. Okay, so these are the overall review of in problem 5.13. Same procedure you have to do. You have to find some masses of mesons, some pseudoscalars, some vector. Their quark and gradients is mentioned in this problem, but the constant you have to know that mass of meson, mass of up quark and down quark is always 308 mega electron volt per c square. Mass of strange is 483 mega electron volt per c square, but mass of charmonium is 1250. Okay, mega electron volt per c square, while mass of bottom quark you can say is 4500 mega electron volt per c square. Okay, now move on towards our 5.15 problem. In this problem there says that you have to write the wave function of your meson. So if you want to write the wave function of meson, so you know that how you can write the wave function of meson, color wave function. So the color single wave function of meson is written by this: 1 by root 3 r, because these are mesons, so mesons must be combination of quark and their anti-quark. So r is quark and r and bar is their anti, so g bar plus b bar. Similarly, in problem 5.16, you have to write the wave function, a color wave function of baryons. So first of all, for the case of color wave function of baryon, you have to write it as like this: 1 by under root 6 rgb minus rbg. Okay, similarly some g, then rb minus g br. Similarly b rg, similarly minus b gr. So this is the wave function of the baryons color wave function. Okay, but how you can write the wave function of baryon octet? If you have baryons and if they are octet, because you know that baryon can either be octet or decuplet. So if they are octet, so there is a factor of under root 2 by 3 there. And how you can write their wave function, like in spin flavor wave function, how you can write psi 1 2 s, psi 1 2 flavor, psi 2 3 spin, psi 2 3 flavor, psi 1 3 spin, psi 1 3 their flavor. Okay, so this is how you can write the baryon wave function of okay, in term of color spin flavor functions. In this problem, you must have to consider that this, if this psi 1 by 2, their product is psi 1 by 2 spin spin multiply and they are same, so they are orthonormal states, so equals to 1. If psi 1 2 multiplies by psi 2 3 next to it, 1 2 next to it is 2 3, then it is minus 1 by 2, and same for if 2 3 s goes to 1 2 s, same answer. Okay, but what if separate parts like 1 2, not 2 3 goes it 1 3, so 1 2 1 3 always equals to 1 by 2. Similarly 1 3 1 2 is also 1 by 2. Also separates are this 1 3 and 2 3, these are also far away, so these are also 1 by 2 equals to 1 by 2. Only the psi 1 2 and 2 3 are minus 1 by 2, all others are 1 by 2. Okay, same these are for spin, and same answers for the case of flavors if you are taking flavor parts. Okay, now in you have to check example 5.1 from book Griffiths. So this is also very important problem. So in this, what you have to do, you have to find write the wave function, baryon wave function, spin flavor wave function of delta plus with spin down, because you know that delta plus is a baryon and it's a decuplet. So how you can write their wave function? Their wave function can be written as this, because this is a decuplet, so it's 3 by 2, because you have to write it by my spin down, so that's why minus 1 by 2. The spin is mentioned in the problem. Okay, so because this is the baryon decuplet, so there is no factor of under root 2 by 3 in the wave function, and there are factors of 1 by under root 3 which each terms of spin and flavor. Okay, so from there how you can write the this. So in example 5.2, what you have to do, you have to write the spin flavor wave function of proton with spin up. So proton is basically baryon and this is from octet, so that's why there is 1 by 2 here, and when you have to write it by spin up, so that's why 1 by 2. This is baryon octet, so that's why there is a factor of under root 2 by 3 there, and 1 by under root 2 terms all with all the corresponding spin flavor components. Okay, in baryon decuplet there is a factor of 1 by under root 3 with all the spin and separately for flavor components, but in uh, baryon octet there is a factor of 1 by under root 2 which each terms. Okay, what is the basically spin of proton? You can say photon. So photon has spin 1. This is a vector. Okay, photon has spin 1. Okay, and because it has a spin 1, then you can say that there are 3 photons emit. This is from triplet configurant. Okay, and how you can write their annihilation part? Alpha 4 mc square 1 divided by 4 n cube. Okay, for L equals to 0 and S equals to 1. Okay, so this is what we are discussing about. Now move towards next. So in problem 5.19, you have to find the magnetic moment of proton. First of all, you must have to know how you can write the magnetic moment of up, down, and stage quark. For the case of up quark, your mu u can be written as 2 by 3. You can write it as like 2 by 3 e h cut divided by 2 mu c squares. Okay, c. Similarly, for down, the magnetic moment can be written as minus 1 by 3 e h cut by 2 md. Md, mass of down quark, c multiplied by c. Similarly, for the case of strange quark, you know the charge is minus 1 by 3. Okay, so that's why you can see here is minus 1 by 3 eh cut 2 m s and c. Okay, but what if you want to find the magnetic total the magnetic moment of this. So the formula of the total final magnetic moment is this: 2 divided by h cut summation I is equals to 1 to 3, because there are 3 quarks in baryons. Okay, because you have to find the magnetic moment of proton. So proton is a baryon which contains 3 quarks. That's why I equals to 1 to 3. Similarly, you have to take multiple with respect to mu I s I z. Okay, and you can find magnetic moments for a b c and different components separately. And final, if you want to find the total magnetic moment, then you will sum up all the magnetic moments to get the total magnetic moment of that proton. Okay, so let's move towards problem 5.22. So the formulas used here is that in this problem you have to find the masses of baryons. Now in previous problem we find the mass of mesons by looking a formula similar to this formula, but this is for mass of baryons, because in baryons there are 3 quarks. So there are 3 mass include, as you can see, m1, m2, m3 and a prime. But a prime has different value. In previous, a prime has a value of 159 bracket 2 mu divided by h cut whole square mega electron volt per c square. But here value is 50 bracket 2 mu divided by h cut whole square mega electron volt per c square. Okay, and again there is a factor of s1 s2 divided by m1 m2 plus s1 s3 divided by m1 m3 plus s2 s3 divided by m2 m3. So these are the factors. Okay, so but here in this problem you have to find the mass of this cascade. Before solving that, you must have to know about the ingredients of cascade. In cascade you have two strange quarks and one up quark. So m1 m2 you have to consider strange, and m3 you have to consider up. And in case of baryon, the mass of up down is different, strange is different. But while in case of mesons, the mass of up quark is 308 mega electron volt. But in case of baryon, the mass of up and down quark is 363, okay, mega electron per square. And the mass of strange is 538 in case of baryons. But in case of mesons, you know that this value is 483, but here is 538. Okay, and the product of s1 s2 and s1 s3 and s2 s3 always equals to h cut square by 4. And the value of once you take the LCM here, and these values add in numerator, and these value must be equals to minus h cut square. So this is how you can solve this problem in by using these formula. Next, move towards chapter number 6. In chapter number 6, we have some important formula problems. Okay, from book Griffiths. So here is problem 6.1 from book Griffiths. In this, he's saying that just to you have to prove this tau equals to 1 by lambda. What is tau? Tau is basically the mean life, which is basically the half life, and lambda is basically the decay constant. You have to prove this. How you can prove this? You have to prove this by this equation: nt is equals to n naught e power minus lambda t. Okay, and if they ask for to find the number between t and d and t plus dt. So what you have to do, you have to just minus the value of nt minus n t plus dt. For t plus dt you have to put the value here, t plus dt it becomes, okay, by taking common, and then you have to minus after get. So after getting value of this, you get the value of probability. So but in last you have to put that value of probability in this formula to gain the final answer of the this term half-life. Okay. Okay, in problem 6.2, again, he's saying that scientists mostly use half-life instead of mean life. So he's saying that you have to prove again a half-life in term of tau. Okay, so if half-life, so here is t initially and t equals, here is t initially, but if once you put t 1 by 2 here, then t 1 by 2 always equals to 1 by 2, and not cancels with other side, and you will take this the exponentials comes up, take ln of 2, so take logarithm to cancel the exponential, and you will get this. Okay, so t 1 by 2 always equals to 1 by lambda ln of 2. Okay, so half-life formula is this. You can see the half-life formula is this. What is the formula of half-life? You can see ln of 2 divided by 1 by lambda. Okay, so in term of tau you can write, because 1 over lambda is always equals to tau, so 1 t half-life equals to tau ln of 2. Understood? In problem 6.3 you can see that the muon half-life is given. which is 2.2 into 10 raised to power minus 6 seconds. And but here is the value of muon half-life is not given in problem. Okay, the only time is given, and he's saying that how many muons left after this time is given in the problem, and but the half-life of muon is not given. In B part he says that how what is the probability of pi minus decay more than 1 seconds, and the half-life of pi minus is also not given. So these are the values you must have to know. So the half-life of muon is 2.2 into 10 raised to power minus 6, while the half-life of pi minus is 2.6 into 10 raised to power minus 8. Okay, you have to take this. In B part you have to take the probability. So probability formula is this: e power minus lambda, and 1 lambda is equals to 1 by tau. So probability formula equals to e is equals to minus 1 by tau. Okay, tau is basically half-life, but he's asking about to find your expression in power of 10. So how you can change your exponential in terms of 10 power. So there is a relationship of changing your exponential in term of power of 10. So so e power x must be equals to 10 power x log of e. Just have to put the value of x here, 10 power, and log of e, multiply log of e by value of x which is in your power. You will get 10 power. Okay, so this is how you can do. In problem number 6.4, the relation is this given: u equals to under root r square plus m2 square c square plus r square plus m3 square c square. This is given. Okay, the only thing you have to prove is a large equation mentioned in question. For to do so, you have to use u value is m1c. The fingertips problem, the finger rules is that you can say the thumb rule is this, like you have to follow these steps. First of all, you have to square root on both sides of this equation. After taking square roots, you have to what you have to do, you have to take c common. After taking c common, what you have to do, you have to divide by 2. After divide by 2, you have to take again square root. So square root both sides, divide by c, again you have to divide by 2, then again square root. Okay, so move on towards problem 6.7. In this problem, what you have to do, you have to prove for cm frame and lap frame. The only thing you have to know about in this problem is that in problem this you must know the value of p1 and p2. In case of cm frame, the value of p1 is e1 divided by c comma p1. Okay, while the value of p2 is e2 divided by c minus p1, because in cm frame p2 is equals to minus of p1. Here is initially p2, but it converts into minus of p1. The key point in this is that you just have to multiply the cross terms, this term with this term and this term with this term. Okay, and there is another formula for m1 square c square and m2 square c square. The only thing is that the square of these, and with minus signs with p, you can see e1 square by c square minus p1 square for this formula, and for this is my e2 square divided by c square minus p1 square. But in this scenario, what you have to do, you have to full multiply this by this and this by this again, and then this by this and this by this. So these formulas you have to know, and you know how to multiply, you can easily get the expression in cm frame. Here in this problem also asking for lap frame. The lap frame p1 is same, but particle 2 is as at rest in case of this lap frame. That's why you can see once you open e2, you know that e basically equals to mc square. So e2 becomes equals to m2 square c square, sorry, m2 c square. Okay, the denominator c, so c cancels with upside c, so it becomes m2c, and particle 2 is at rest, so that's why their momentum is 0. In problem number 6.8, asking about to find the diffractional scattering cross section in cm frame and lap frame. Basically, in cm frame, the diffractional scattering cross section can be written as this formula: d omega by d sigma over d omega. equals to h square c divided by 8 pi whole square. Okay, h square c divided by 8 pi whole square. S amplitude square divided by E1 plus E2 whole square. PF divided by PI. Okay, so this is how you can write the diffraction scattering cross section in terms of CM frame. But they are also asking to write in lab frame. In lab frame, what in this problem they say that the target particle is so heavy and they are at rest. So if target particle is at rest, so it barely moves, and so particle 1 bounces off from particle 2. Okay, hence the energy is not changed. So if the energy is not changed, so momentum is conserved. P of I must be equals to P of F. So if both are equal, so they cancels in this, so that's why you can see no momentum terms here, because there are two different particles, particle 1 and particle 2, then their statistical number s is always equals to 1. So you can see s equals to 1, there is no s. But in case this your particle 2 is so heavy, that's why the incoming particle energy is not able to change the energy of that. So that's why ea is negligible. That's why you can see e1 is gone and there is only e2. E2, you know that mbc square, E2 equal to mbc square. So this is how you can write in term of lab frame is d sigma over d omega must be equals to h square c divided by 8 pi whole square and m square divided by mbc square whole square. And lastly, we discuss some Gell-Mann matrices. In Gell-Mann matrices, these are some constant values: lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, lambda 6, lambda 7, lambda 8. Okay. How you can remember these? I'm just telling you to how you can remember these if these are not mentioned in your paper. So you know that lambda 1 is always these are some 3 cross 3 matrices, but you know 2 cross 2 matrices. Lambda 1 is always equals to 0, 1, 1, 0. This is you know. All other terms are 0. Similarly, lambda 2 is this, you know that minus iota iota here. And lambda 3, you know that always 1 minus 1, all other are 0. But what you can do in lambda 4 is that you have to move this and this one to the cross ends of this and this. So you can see 1 1 is got here and 1 1 goes to here. 1 1. Again minus iota here and iota here. Minus iota iota. All others are 0. Okay. And what you can do in lambda 6 is that you have to stretch it in downside. This stretches in downside. So 1 1. You can see 1 1. Again minus iota iota in lambda 7 and minus iota iota. But lambda 8 is different from all. You have to remember that this is equals to 1 by root 3, 1, 1 minus 2 in diagonal, and all others are 0. How you can solve the Gell-Mann matrices by using this formula? F of I comma f of j must be equals to iota fijk fk. Okay, and how fk is expressed? This fk basically equals to 1 by 2 lambda k. Fk equals to 1 by 2 lambda k. If f1, then 1 by 2 lambda 1, depends on the values. Okay, now move on towards next some Callan-Cardan equation and Dirac equation. So what is kg equation? How you can express your kg equation? So kg equation can easily be expressed by using the Einstein relativistic equation. You know that E is equals to p square c square plus m square c4. How you can start? By putting the values of E. You know E equals to iota h cut partial by partial t, and your p equals to minus iota h cut partial by partial x. Or you can also express p is like that, p equals to minus iota h cut delta. So by putting the values of p and e in your Einstein relativistic equation, you can easily express your kg equation by do some simply multiplications. Okay, Dirac equation. So what is basically kg equation? How you can remember is that del square psi minus 1 by c square partial square psi divided by partial t square minus m naught c divided by h cut psi equals to 0. Okay, minus m naught square c square divided by h cut square psi equals to 0. So this is how you can remember. Similarly, the Dirac equation. How you can express the Dirac equation? Again, you have to solve from Einstein relativistic equation, E square equals to P square C square plus M naught square C power 4. Again, you have to put in the values of P operator and E operator, which I mentioned you before. And here you have to use Dirac assumptions. Okay, we will solve this all in our upcoming videos. So till then, you have to stay upon only these formulas. Okay. So what is basically Dirac equation is that E psi equals to plus minus C alpha dot P plus beta M naught C square psi. Okay, so this is the Dirac equation, and you can see E psi equals to H psi, the Schrodinger wave equation. So this becomes H. So this inside value is basically the Dirac Hamiltonian. So how you can write in term covariant form, gamma mu partial mu plus m multiplied by psi equals to 0. So this is how you can write Dirac equation. Okay, so in Dirac equation, the key multiples is that, so to find the Dirac equation covariant form, the thumb rules are this: you have to multiply by beta divided by h cut c. Then from in time part, you have to move iota downside, and beta square must be equals to 1, and you have to open this del by partial xk, which is the space part. Okay. Okay, and here is alpha k iota beta must be equals to minus gamma k, and beta must be equals to gamma 4. Okay, so this is how you can use. Now move towards our last important part, and our last important part is basically the raising and lowering operators. So raising and lowering operators, the formulas, these three we have to use. For case of I plus minus, the formula is F1 plus minus iota F2. For the case of V plus minus, the formula is F4 plus minus iota F5. Similarly, for the case of U, the formula is F6 plus minus iota F7. In I, you use 1, 2, then in not U, then you have to move on V. Okay, I, then V, in V you have to use 4, 5, and in U you have to use 6, 7. Okay, and similarly in case of these matrices, these are some different matrices. In this you have to use I plus minus equals to I1 plus minus iota I2, and in this the values of I are different. The value of I1 is, what you have to do, this 1 1 you have to move in 1 1 here, this minus iota 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 iota, and here is 1 minus 1, and that minus 1 goes to downside. So these are some problems which you have to use in these for these formulas which you have to use in problems. Okay, so in upcoming videos we will solve separately one by one each problem. Okay, so it's quite easy for you to understand. So this is only introductory lecture of the formulas list which we are going to use. Okay, and these are very very important to remember. Without these formulas you can unable to solve the problem. Okay, so that's why this is some introductory video. In upcoming videos we will solve. Till then, take care and Allah Hafiz.